But no, my name is Alex Gurvich. I'm a fifth year grad student at Northwestern University. And today I'm really excited to share just a very small subset of the results of a paper that we published about a year ago on star formation in galactic disks. All right, there we go. Um, Everyone saw it advance? Good, excellent. Star formation in galactic disks. Star formation is very inefficient in galactic disks. So what do I mean by that? So I mean that if you took all of the gas in one of these galaxies and you let it collapse under the influence of its own gravity, it would turn into stars very rapidly, something like 100 million years. But instead, we see these star-forming galaxies that persist for billions of years, right? These gas depletion times are much longer than that. And so there must be something going on that is preventing the gas from just catastrophically collapsing and forming stars. So the Kennecott-Schmidt relation is an empirical relationship between the gas surface density and the star formation rate surface density. And it relates it through the free fall time of that gas and an efficiency parameter. And so when I say inefficient, I mean like pretty inefficient. I mean something like 1 to 2% of the gas and its free fall time is converted into stars. And so the Kennecott-Schmidt relation is something that people have been looking at for a long time. But just in the past few decades, there's been a push to look not just at averaging over the entire galaxy, but if you break up that galaxy into small patches, what people were finding is that those patches would, on average, lie along the relation. But as you looked on smaller and smaller scales, there would be more and more scatter from that average. And so there's become a whole industry in explaining both the mean relation and the scatter. And one class of models that performs really well at explaining the mean relation are so-called equilibrium star formation models. And they get that name equilibrium because of one of the basic assumptions that your galactic disk is in a state of vertical hydrostatic equilibrium. And the picture you should have in your head is that the gas wants to collapse towards the midplane, which compresses the gas there, then triggering star formation. So those new young stars will then generate pressure through stellar feedback. And if you assume that that pressure balances the weight and you have a nice steady state, then you can write the weight as a quick estimate, just like the plane parallel geometry type weight, and assuming that the pressure generated by the stars is just proportional to some constant amount of momentum per stellar mass formed, you can get a similar expression relating the gas surface density to the star formation rate surface density that predicts the correct scaling and normalization of the Kennecott-Schmidt relation with just like very simple ingredients. And one of the really nice things about this class of models is additionally, the Kennecott-Schmidt relation is observed to have a slightly different slope in starburst galaxies, a little bit steeper, which we think are also very gas rich. And so you can see here that just from the composition of the galaxy, that falls out naturally, is that as your gas fraction increases, then the slope will get steeper, the relationship between the star formation rate and the gas surface density. Okay, so with that context out of the way, there were two main questions that we tried to tackle in this paper that I'll be able to cover today, but there's a whole bunch of other stuff, so I hope if you're interested, you'll go take a look. So number one, are these basic model assumptions, these two equations that I was talking about before, really satisfied in the fire simulations? Because there's some really strong assumptions that we're making about the geometry of the galaxy. I only talked about one single kind of pressure, saying everything is turbulent pressure generated only from stellar feedback. That all the time scales involved are matched such that, everything's happy. It seems almost too good to be true. And then number two, if and where there are deviations from this equilibrium, could that then tell us something about the scatter, right? Because so far everything I've been saying is just about the average relation. So before I move on, I want to introduce the fire simulations. So the tool that we use to try and approach this problem. fire simulations are a set of cosmological hydrodynamic zoom-in simulations. So what that means is that they're high-resolution simulations of individual galaxies that include their cosmological environment. So that means that they have, accretion from the IGM, they have their own satellite galaxies, they have a self-consistently formed CGM, uh, and they'll have mergers, and all of this from initial conditions taken like just after the Big Bang from the CMB. And so, when I say high resolution, I mean these galaxies have high enough resolution that we can resolve individual star forming regions. And so we can use a star formation prescription that doesn't have to have any like bigger laws baked into it, that's just a function of the stuff there. And so when we couple that with a set of comprehensive stellar feedback prescriptions that are calibrated from even higher resolution simulations, what you end up with are these beautiful disk galaxies that emerge in the simulation volume totally naturally, right? And without having that lie on the chaos relation, without having to imprint the chaos relation in your star formation prescription and that form disks without having to start from initial conditions that are already in hydrostatic balance or like don't include the CGM or something, which is what's been done so far before we came along. And so this is one of those disk galaxies at redshift 0. We're looking at it edge on. So in the top panel, I'm showing a gas projection. It's a mixed projection that shows the density and temperature. So the brightness of each pixel is proportional to the density, and the color is proportional to the temperature. So these bright blue pixels represent dense cold clumps, and these greener, fuzzier pixels represent a more diffuse hot gas. And what I want to draw your attention to is this really complicated phase structure, right? This is very far from like a single phase gas, is that you can see these like little dense clumps surrounded by a warmer, more diffuse envelope with like little pockets of hot gas near the midplane, like a little hole kind of blown in it, and then surrounded by a halo of hot gas around it as well. And so, this really, I think, goes to show that the fire simulations, the fact that they lie on the chaos relation, but are so complicated, really offer an ideal laboratory to answer this question about the origin of the chaos relation. And so to address those questions, what we did is we just went in and tried to measure what the pressure and the weight were in stacked slabs, columns of slabs that we tiled across the face of the galaxy. And so we used 4 different tilings to emulate that same different length scales that the Koenig-Schmidt relation was averaged on. And so here I want to really consciously change my vocabulary and introduce a concept that might be new for some people. And I want to talk about something I'm going to call dynamical equilibrium versus hydrostatic. So hydrostatic equilibrium comes from this equation of hydrostatic balance. You're probably familiar with it from like stellar structure or something. And all it does is it relates the weight of overlying gas, or this is the non-integrated form. So it's the weight of gas in like a shell to the gradient of the pressure, and that those two should balance each other. And so here the pressure term has components that look something like a thermal pressure. And maybe, depending on your situation, you might have some kind of like turbulent support as well. So I want to contrast that with the more general dynamical equilibrium, which comes from the equation that gives you hydrostatic balance, the Euler momentum equation, that has this additional convective term in it. And so what you can think about this additional term is just another pressure term that represents like a bulk motion through the cell, right? And so each of these terms really represents kinetic energy on different length scales. So a thermal energy is like very, very small length scale, right? Like atomic, like statistical mechanics type length scale. Whereas like a turbulent or velocity dispersion support is really measuring kinetic energy on length scales of like eddies that are contained inside your box, maybe as big as, but like on less than or about the same size as your box. Whereas your bulk pressure is going to be something that's like an eddy that encompasses your entire box. And so I make this distinction because as we change our grid scale, we're going to see that the dispersion and the bulk pressures will swap kinetic energies, that'll be distributed between them as a function of grid scale, but that the total kinetic energy will be conserved. One last thing that I wanted to mention is that if we look at this equation, it automatically goes straight back to hydrostatic balance, right? If the bulk flow is zero. If there is no bulk velocity, no average velocity moving through your slab, then you have exactly the same situation that we were in before. But if
Can I ask a quick just
Sure.
clarification question? When you're talking about your grid scale and your boxes, are you
Yeah.
actually talking about this? Okay, you're talking about this grid that you've overlaid, not actually
Yeah,
like the
sorry.
grid in
No, 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 no. Not
the,
like the simulation resolution or
yeah.
something. Yeah,
Okay.
so because we use a Lagrangian
Right. Of
code where
course.
we have like actual particles and stuff. Sorry. Yeah,
Got
I
it.
mean
Okay.
the actual grid that we're measuring the pressures on.
Perfect.
As we look on smaller and smaller scales, you're going to subsume more and more eddies, right? So
Got
your
it.
bulk pressure is going to be higher because there's smaller structures that will encompass your smaller grid cells.
Perfect. Thanks.
Yep, no problem. So it would go back to hydrostatic equilibrium if there were no bulk flows, but that's just not what we see. Even in a steady state, if you're averaging over a long period of time, the bulk velocity in these galaxies that form time steady and stable disks is not zero. What we see instead is a time steady hot galactic fountain, right? So if we look just above the midplane, there's a pretty substantial bulk velocity that's positive, so we're moving away from the midplane, and then that'll change sign as you get higher. Then if you look below the midplane, you get the mirror image, right? So you're still moving away, but you're just moving down. And the picture that we have in mind when we see this is that you have hot gas that's being launched very close to the midplane, goes up to some height, will slow down ballistically, and then join a coherent inflow of warmer gas, which will then be recycled down towards the midplane. Okay, now that this picture is maybe a little bit more complicated than we expected, we can still ask the question, are our two equations satisfied? But we have to do so in the context of not just the turbulent pressure, but the total pressure, including the bulk flow and thermal pressure terms. And so if you plot like a scatter plot of the total pressure at the midplane versus this estimate for the weight, G sigma disk, sigma gas, we do see that these two correspond pretty tightly to one another. And if you plot again that same total pressure, including the bulk velocity, versus the star formation rate surface density, they still are proportional to one another. So we can connect in this like very simple way the gas surface density to the star formation rate surface density. But the system is clearly much more complicated than we originally had in mind. But we can do better than just estimating G sigma disk, sigma gas as the weight. In each of our columns, we can actually integrate what the weight of the overlying gas is and compare it to the pressure at that height. And so here what I'm showing is in 3 different radial annuli, and for all 4 of our different grid scales, that pressure to weight ratio as a function of height. And so basically everywhere in the disk at all heights and at all radii, these two are very close to each other. The ratio is almost exactly 1. Now, probably a lot of you are focusing on this feature right here in the middle that seems like in contradiction with the statement that I just made. If I have time at the end, I'm happy to talk a little bit more about this, but there's a term missing actually that we don't account for in the Euler equation, and that's for an arbitrary momentum source term. And just based off of the numerical implementation of our stellar feedback, we do inject momentum directly into the simulation around young star particles. And so near the midplane, we expect there to be a little bit of a dip wherever there's active star formation, and then subsequently where we're actually injecting momentum. And because the kernel that we inject momentum in is finite, if it's comparable to the scale height, it's going to show up here as a little dip. And so the magnitude of the dip, something like 20 to 30%, is consistent with the amount of momentum that we expect that we're actually injecting um, from our stellar feedback routine. So that's my short version. I'm happy to talk a little bit more about it if people are curious. But now I want to talk a little bit more about deviations that we do think are real. Because I've just told you that everything is like almost in perfect, dynamical equilibrium, if you average over the face of the disk in these wide radial annuli. But if you plot this pressure to weight ratio in a map, this grid over the face of the disk, and so for each of our different grid scales, which is what we have here, and then here on the left, I've just done an identical rendering as before, just flipped it face on just to help orient ourselves and put contours around the dense gas so we can figure out what's going on. You'll see that it's not that everything is in this like little whitish yellow area. There are really significant deviations, especially on small scales, something like a factor of 10, in either direction. And there are these hot and cold spots. And in particular, what we noticed that stood out are these like big blue, under pressurized regions that correspond to these voids between the spiral arms. And so even though on average you might hit pressure balance and dynamical equilibrium, because of non-axis symmetries in your galaxy, individual patches are going to fall somewhere on either side of your average dynamical equilibrium. So if you look in one of these radial annuli and you plot something like the standard deviation as a function of radius, you can see a systematic increase in the size of the deviations as you're looking on smaller and smaller length scales. Now, hopefully this reminds you of something that I was talking about a little bit before, and I hope that you'll indulge me in a little bit of eyeballing. And so if you compare the scatter that we observe in the KS relation to the scatter in the pressure to weight ratio that we measure in the simulation, and here I'm just trying to pick a round number that looks something like it, something like half a dex for the 2 kpc length scale. And you see it's like on average, it kind of falls in between the 3 and 1 kpc curves here on the left. You do the same thing for the 500 parsec length scale, and you see that it also falls pretty close to the 100 and 300 parsec curves for the amount of scatter and the pressure to weight ratio. Now, the point I want to make here is not necessarily that there's a one-to-one mapping between the pressure to weight ratio scatter and the scatter we observe, because there's tons of other observational factors that are going to contribute to the scatter. But rather, that scatter and the pressure to weight ratio represents a minimum theoretical uncertainty in the KS relation that comes from the ISM's ability to even self-regulate to a state of dynamical equilibrium. And for whatever reason that might be, that an individual patch might not be in perfect equilibrium, be it like a difference in time scale from stellar feedback and star formation, or from like a gravitational collapse on a dynamical time or something. What we would predict is that the ISM is not in a perfect state of stable hydrostatic balance, but that it is on average in dynamical equilibrium, and it is constantly over and undershooting in an individual patch. And so I'm going to bring up those main questions again and try and answer them. So number one, are these basic models assumptions satisfied in the fire simulations? And I'd say, yeah, they are, just not really in the way that we had originally expected. Indeed, that very simple model was a little too good to be true. Instead, there's actually a dynamical equilibrium. And it's not just the turbulent pressure that matters, but there's these steady state bulk flows in and out that really need to be taken into account. And then number two, where there are deviations from this equilibrium, are they connected to the dispersion and the chaos relation? And I'd say, yeah, I mean, at the very least, the pressure to weight ratio represents a theoretical minimum, as I was saying. So, we expect that the chaos relation is never going to be perfect along a single line, and not just because, we haven't built good enough telescopes. So since last year, when we published this, I've been working on trying to take this pipeline, which currently, which not currently, but as of what I've shown you, really assumes a disk geometry and really only makes sense to apply at low redshift after the galaxy has settled down. To take it to the high redshift galaxies, which the fire simulation would predict have burstier star formation rates, are more irregular, and in general are just more chaotic dynamical systems, which certainly are not in hydrostatic balance, but we might be able to find that they are in dynamical equilibrium. And so we want to ask that question, is the fact that, this is that the star formation rate scatters a lot, but still kind of about an average, could that be related to the fact that it's in dynamical equilibrium? And how is that related to the formation of a galactic disk? And so is this assumption, this very strong assumption of a disk geometry, really necessary to the story, or is there something more basic going on? And so, yeah, here I'm just showing that at the same time as the fire simulations would predict that these galaxies have their star formation rates really nail themselves down to a single value, and become more time steady, is the time when they form galactic disks, where all of their angular momentum is concentrated in rotation about a single axis. So this diskiness parameter represents the ratio of angular momentum in the z direction to the total. And so we hope that to get these results out very soon in the next couple months. I'm writing and I'm iterating with my advisor, so hopefully you can keep an eye on the archive and see something soon. I'll throw up my conclusion slide again, and I guess with whatever time, I'm happy to take questions.
Great, thank you. I'll clap for everyone. Yay, thanks so much. Okay, cool. Yeah, this was great. Wow, we were treated to two very gorgeous and interesting talks today. So that was totally awesome. I'm going to let John go first, since you went first last time, Brian, and you can go second. Okay, John.
All right. Great. Hi, Alex. Good to see you. Really, really great stuff. I have like a million questions, but maybe I'll just ask one. So in the plot you showed of like inflow and outflow as a function of height, both above and below the disk, I was intrigued that it was so asymmetric. Like to 0 third, I would have expected above and below to be sort of indistinguishable. But I'm wondering, like, is this taken at like one particular moment, and the scatter is like from all the patches, or is this like averaged, like over how much time is this averaged?
Sorry, yeah, I definitely went through fast on this. So yeah, it's averaged over a 600 million year period, just weighting each of the different grid slabs equally. So it's not just a single time, but it's averaging over a larger swath. So like maybe one or two dynamical times around.
Okay, and yet it's still so asymmetric, which is
I guess I'm curious what asymmetric feature is standing out most to you? Because I guess for me, what I see it as like kind of mirrored, but still mostly symmetric.
Yeah, like within a scale height, I agree, it's mirrored, but like the sort of fountain at like 5 to 10 scale heights becomes very different.
So you're looking at like
top versus bottom, yeah.
Yeah, here I see what you mean. Yeah, I mean it would certainly depend on the exact structure of the inflow, and exactly, what's being mixed and how stuff is cooling, and it's definitely not something that we've looked at too closely. But Yeah, I guess I think I see now what you mean in terms of this.
Okay.
Yeah, it's a good question.
Well, I'll turn it over to the next person. Thanks.
Thanks. I was just teasing. That was super fast, John. That was a great starting question. Great. Brian.
Yeah, thanks for the nice talk. I was curious about the role of cosmic ray pressure. These high
Yeah.
star formation rate galaxies, maybe they cool fast and don't matter, but I can imagine that might add some damping effects to all this fluctuation.
Yeah. So I wonder. So so TK Chan has looked exactly at this, and so he has a follow-up paper where he does a very similar analysis, but includes the cosmic ray pressure. So these simulations don't include any cosmic rays. Uh, the short of it is that very close to the midplane, there's not much that the cosmic rays do. So they end up streaming pretty much out into the CGM without interacting much, and so any changes near the midplane end up just an effect of the change in the way that you're accreting gas, or like kinetic energy is being generated and then transported into the disk. But there is a pretty big change out at larger scale heights. And so one thing that I didn't show is that, one thing that we look at is how the pressure breaks down between different terms as a function of height. And at large heights, because the gas is mostly hot, unsurprisingly, the dominant pressure is the thermal pressure. But when you start to include cosmic rays, that becomes about the same magnitude as the thermal pressure out there, because it's providing a non-thermal support, and so your gas is actually able to cool and get a little bit colder, like so changing phases to like the warm phase, and it doesn't need as much thermal support to stay out there in the halo. So yeah, cosmic rays are definitely an important part of this story. What I would say is that at the midplane, and in terms of the Kenneget-Schmidt relation, I don't think that they're going to play much of a role in terms of setting the normalization or having to worry too much about like my two very simple expressions. But they're definitely going to change the phase structure by letting gas at larger heights cool to lower temperatures. And they're definitely going to change the way, just a little bit, I think TK found, the way that kinetic energy is distributed between the bulk flow and the dispersion pressure. Does that make sense?
Yeah, thank you.
Great. Matt.
Alex, always great to see a talk from you. So I know in a lot of this analysis, you had a density cut as well as differentiating these things. And for the most part, I agree that, it's not really going to affect the hot or the warm, but in the cold phase, one of the things I think is very interesting is that signature, which I really like the explanation of that sort of dip right in the center at the midplane is, the direct injection of
Yeah.
feedback. How much do you think is also missed in terms of as you get to the midplane where the gas is densest and coldest?
Yeah.
That
Am I
you're
just
sort of missing that?
excavating, yeah, that extra pressure? That's a great question, Matt. So it is something that we looked at. So what Matt's referring to is I didn't really talk about what the difference is, and I went very fast. This is definitely a subset of a longer talk. Um, so we have these definitions for the different phases of gas, but we also exclude any gas that's colder than like 50 per cubic centimeter, because that gas is going to be bound in dense clumps that doesn't participate in this vertical pressure balance, this dynamical equilibrium. Instead, it's governed by its own internal dynamics. But the question is that, very close to the midplane, you could be subtracting out some temperature by pretending or subtracting out some pressure, some dispersion pressure potentially, from pretending that gas actually isn't there. So we've relaxed that limit, that 50 per cubic centimeter. So we've included it all together. Actually doesn't make much of a big difference. So here, I'm looking at this cold panel on the left. And so, near the midplane, most of the pressure in this cold phase is coming from dispersion pressure. And so you might think that, there's some extra dispersion coming from these bound clumps, but it doesn't end up getting coupled to the larger volume of the gas. And so we've done it without the cut. We've gotten the cut as low as 1 per cubic centimeter, without making too much of a change. But then once you start getting around 1 and lower, then you start excavating that gas near the middle, and then you start to see this pressure differential coming from losing it. So yeah, it's somewhere, I think it's either 1 or 10 per cubic centimeter. It's like
So
that's the region where you start taking out the cold phase that you do need.
okay, so I would imagine there it's the difference between you're following like the really dense nuggets that might be having some dispersion, but it's not really most of the momentum versus like, oh yeah, I'm excavating whole clouds, which
Yeah, exactly. Yeah, is this like colder, more diffuse gas? Exactly.
cool. Thank you. That was a question that I'd meant to ask you in the past.
Great. Alberto.
Hey, Alex, thank you for the talk. So I was curious about your face-on view of the out of equilibrium region. And I don't know if I got the right
This.
impression, but looking at that, it seems that most of your out of equilibrium regions are interarm
Yeah.
regions, no?
Yes.
So why is that? Do you have an intuition as to why that's preferentially happening in the interarm and not in the dense part?
Well, I can say, for sure that I have like 3 or 4 answers here. So I'm gonna try and pick the top two, and I'm gonna do my best to explain them. So number one, like I said before, at least the under pressurized stuff, I do have an intuition for, right? So this is stuff where the weight there's a stellar disk that exists that is there. So there's a weight that we're measuring based off the diffuse gas, but that gas is mostly underpressurized just because the density is so low because it's been excavated by stellar feedback at the edges of the arms. And so even though the weight there is set by the density of that gas, that's where the outflows are coming from. So I guess really, where you're getting this underpressurized stuff is just there's not much material. And so you're just not really sampling very well. That explanation didn't really go where I wanted. But the to answer your another part, it's really the dense star-forming gas that we expect to be in this pressure equilibrium, right, where the time scale is small and so comparable to like the feedback time scale, and the density is high, and so that's where we expect like Toomre Q to be a constant, like somewhere around 1. Whereas in these regions where there's a lot more hot gas, that's stuff that hasn't been in contact, that hasn't heard any information about star formation in a long time. And so for me, when I look at the stuff between the inner arm region, I see that as like a relic of a previous time, either before or after, right? That's either gonna that's been affected by feedback from before, and has been kicked out and is in between these arms now, or is like kind of on its way merging in, with the galaxy having like reaccreted or something.
I
So
think
whereas the stuff in the spiral arms, that's the stuff that's actively star forming and is closer into that green, that Goldilocks zone of the different time scales.
I mean,
That's the best. That's the best I have.
it's interesting to me that the lack of equilibrium is related to the arm interarm. It also seems to be increasing as you go farther out in radius, no?
In terms of the going further out in radius, I do actually think that that's from the momentum source term, believe it or not. So where do I have it? Yeah, here. So you can see the same thing happening in this plot, is that this dip. So what I'm plotting in this image is actually average between plus or minus 1 scale height. And so this dip actually takes more, is larger, as you're going further out, or sorry, is larger as you're closer in. Let me start over. This dip is more important where there's lots of star formation and there's a radial gradient in the star formation. And so there's a lot more young stars that are injecting momentum near the center. And so this dip is more important. So we're gonna see that stuff is more under pressurized, which is this like kind of blue square at the center, this blue here, but that's just from the momentum source term, right? This blue at the center. If you're looking out, then you're having larger non-axis symmetries, right, as you're getting further out. And so then you'll see more scatter. But in terms of the actual deviation, I think, the brightness here. I guess maybe you're looking at this bright red spots
Just
here,
looking
and
at
they're
the fact that there is
further out.
Yeah.
Yeah, I mean, I guess to me, I see much more of this cream yellow as I'm looking out, and I see much more of this blue.
I see.
Ah, hey, we're drawing. Hey. Okay.
Anyway, I was interested about your insight. Thank you.
Sorry. Yeah. Thanks.